In this paper, we present TED-4DGS, Temporally Activated and Embedding-based Deformation for 4DGS Compression. Reconstructing dynamic scenes from multi-view videos has long been a central challenge in 3D vision. Such a capability has potential use cases in AR, VR, 3D animation, game production, or film creation, allowing users to observe such scenes from any desired viewpoint. Building on the success of 3D Gaussian splatting for static 3D scene representation, its extension to dynamic scenes, often called 4DGS, has attracted increasing attention. However, these Gaussian splatting-based methods usually require high storage and transmission bandwidth because they involve a large number of primitives and time-varying parameters, which makes real-world deployment challenging. To tackle this problem, we propose a rate distortion optimized compression framework for dynamic 3DGS. Specifically, we quantize and entropy code Gaussian attributes to balance compression and reconstruction quality. The whole framework is optimized end-to-end for each scene, and the compressed model can also improve inference speed. Despite its promise, rate distortion optimized compression for dynamic 3D scenes remains largely underexplored in the community. Towards this end, our work builds on a canonical, deformable 3DGS representation, with a particular focus on how deformation is encoded. Specifically, we adopt Scaffold-GS, an anchor-based representation, as the foundation, and introduce a per-anchor embedding design to model temporal deformation. Each dynamic anchor is equipped with a temporal feature, which acts as a soft query to a global deformation bank for retrieving its deformation. This design enables flexible motion modeling while leveraging the spatial sparsity of anchors to reduce the number of deformation-related parameters. Secondly, TED-4DGS assigns each canonical anchor an explicit temporal activation parameter that defines its active duration. This facilitates more accurate modeling of occlusion and disocclusion and prevents the generation of unnatural deformation caused by relocating non-contributing anchors during scene rendering at specific time instances. Lastly, to encode anchor attributes in a rate distortion optimized manner, we propose an INR-based hyperprior to model the coding distributions of anchor attributes for entropy coding, along with a channel-wise autoregressive model that further exploits intra-anchor correlations for more efficient feature compression. Empirical evaluations show that our work achieves very promising coding performance. This strong performance is mainly attributed to our deformation representation, which effectively leverages the spatial sparsity of anchors in 3D space to significantly reduce the number of deformation field parameters, as well as our INR-based hyperprior, which enables efficient compression of anchor attributes. We consistently outperform the competing methods across both datasets, achieving state-of-the-art RD performance. Next, we present the rendering results in temporal activation visualization, with the rendered video shown on the left and the temporal activation visualization on the right. We analyze Gaussian durations, defined as the temporal span between activation onset and termination. As observed in the video, under limited occlusion and disocclusion, most Gaussian primitives exhibit long durations and remain active throughout the sequence. In contrast, primitives that emerge later are activated only during their visible frames via the temporal activation function, eliminating the need to model pre-appearance states or relocate them outside the viewing frustum. This yields more natural motion modeling. Thank you for the attention. For more details, please feel free to check our project page through the QR code below.